All right, so we got about 3 more minutes before the lecture officially starts. So what we'll do today is talk about the exam one to be exact. So that's going to be next Wednesday. So you might want to make sure that you can indeed make it to class next Wednesday. And on Monday, we'll go over a practice exam, which is included in today's text channel already. So just go to the pinned messages. The second one has the PDF of um, exam one from last semester. And this is not a practice, this is the actual exam one from last semester. And you have over the weekend to kind of work on it and see if you can find out, how to answer those questions. Given what we have talked about already, and given what is also included in the exam, there is enough information to solve those problems. The only question is, um, the only question is, can we make all the connections? So on Monday, I'll talk about the solution and how to solve those particular problems. Problems 1 and 2 are the most difficult because you have the fewest known bits, and then 3 and 4 are easier, and then the last four questions, questions 5, 6, 7, and 8, are the easiest because there are a lot of zeros and ones already given, so to figure out the rest should be a little bit easier. So I would suggest you to start from the bottom. You'll start with questions 5, 6, 7, and 8, and then work your way back up to questions 1 and 2. Oh, interesting. Okay. Ah, okay. So I was just reading a DM. That's all right. There we go. Hard to understand. Well, I'm not sure why, but that's how I write. I mean, I did not even try to make it hard. Not logically. Well, you can point out to me how it is not logically making sense. Okay, all right. So I will go over that on Monday. So in case anyone has any comments or questions about what I'm really asking, you can bring those questions on Monday, and I'll give you my solution on Monday. Basically, it's okay. The first part, which is the most difficult part, just think of it as binary addition Sudoku. Yep, that's basically what it is. You know the rules, you know the relationship between the bit positions, and I give you a few known zeros and ones, and you need to figure out the rest. So, how does that sound in terms of explaining what is supposed to be done with those questions? Yeah, just think about as Sudoku. Yep, it's not going to be straightforward, but it does, everything that we have talked about already is enough to derive the answer. So it does take a little bit of time to kind of wrap your head around it. Yes, so it is your job to find a value for each question mark, and the solution is unique. So that's, the other clue is, there's no such position where you can put in a 0 or a 1. They are all unique. There's only one solution for each of those questions. All right, so that is sort of out of the way. We are into the class time now. So I'm just going to write down here, exam 1 is on June 23rd, 2021 from 5:30 p.m. to oops, I almost wrote down 7 to 6:50 p.m. Except for people who have exceptional occasions, and they have already talked to me about that. Um, so this is the start time and the end time of the exam, and the way it's going to go is at shortly before 5:30 p.m. I will share a Google document with every person in the class, and you write your answer in the Google Doc, and then at 6:50 p.m. my script will run and it will unshare that document. And that's how I distribute the questions, and this is how I collect the answers. So I want to make sure that everybody understand the basic rule. This is an individual exam. It is not. It should never be a group effort, or there should not be any collaboration during the exam. Um, there's no copy and paste into the Google Doc, so you have to write your answer entirely within the Google Doc. Now, on the other hand, some people say, but I would like to, handwrite, stuff, on a piece of paper or on a tablet. Can I do that and then paste the image into the Google Doc? The answer is yes, but you will have to do it within the time allowed. So there's no extra time for people who or writing on a piece of paper and then try to copy and not copy and paste, take a picture and then you'll copy paste the picture into the Google Doc. There's no extra time allowed for that. Okay, so you have to factor everything that you need to do and make sure that by 6:50 p.m. everything is in the Google Doc. And when I say 6:50 p.m., I'm talking about 6:50 p.m. local time in Sacramento, um, and it's going to be synchronized with the atomic clock. So I don't. So arguments of, but it is not 6:50 yet. On my watch. On my watch, it's only 6:45. Those arguments will not fly. Okay, so if you need to know what the exact time is, we talked about this in the previous class already. There's a website. Um, your tax money, is paying for that, and it will tell you, what the exact time is, and then you want to kind of leave a few seconds at least, okay, as your buffer, and that should be good. All right. So,
I have a
yeah,
question,
go ahead.
Professor. Can I ask?
Yes, go ahead.
So regardless about the Google document, are you gonna share like on Discord, or are you gonna share like to the Canvas account?
So that will be shared with your apps.losreels.edu Gmail account. Um, I'm not sure, what email you're using for school-related activities, but I will be sending those to the apps.losreels.edu account. So that means you probably want to make sure that you have access to the apps.losreels.edu account. You will receive a notification by Gmail, but at the same time, when you go to Google Doc through apps.losreels.edu, you would also see that document being shared with you at about 5:30.
So basically, we'll have to write our respond through the Google Docs, and that's how you collect it, correct?
That is correct. Yep. So you
Okay, thank
basically,
you.
I would say most people are going to type their answer in because most people can type faster than they can handwrite, but some people may want to handwrite, because they want to present a something that is more graphical in nature instead of using text. So those people would have to they need the extra time to take a picture of the handwriting, and then paste that picture into the Google Doc. So, however you guys want to do it, that's kind of the rule. But there will be no copying and pasting from outside of the Google Doc. Copying and pasting within the Google Doc is perfectly okay. So, as long as the pasted material is your own within the Google Doc, it is okay. All right. Are there any further questions? We'll talk more about exam one on Monday, but I do want you guys to have a chance to kind of practice and kind of work on it over the weekend. So this way, if you can figure out a part of it but not some other parts, you can write down those questions. And we got a question on the text channel. Yes, you do have to show your line of reasoning. So all the questions, basically will tell you that you have to explain how you derive those zeros and ones. You can use a reference system. In other words, if you think, a particular line of reasoning is reused a lot of times, you can just say, look at reason A, okay, or reasoning, item A. So at least, I can tell, how you come to the conclusion that a particular bit should be a 0 or 1. So you do have to show your work. Typically, in my exams, the final answer by itself is worth very little value or no value in some cases. I need to know how you get to that answer. So the explanation of how you get to the answer is very important. All
And
right. Yeah, go ahead.
so regarding this exam, it will be cumulative of the past 8 sessions that we've had, and it should generally involve just the knowledge that we've accumulated over the past couple of weeks, general knowledge, or should it be like we have to really know our stuff? Or
I would say the scope is, everything up to and including signed versus unsigned numbers, and also comparison, binary comparison. So that's the
all right,
scope.
and
Hmm.
sorry, and for the answers, like you said, we can reference. If it's been said a million times, we can just reference it as it is this proof. Or could we do when we're answering the question? Could we also reference sections of certain uh, reading assignments you assigned to us, like in section 4 of the binary additions?
Yes.
It says it
Hmm.
in
Yeah,
much greater detail.
absolutely. So typically, okay, so I'm going to use a little bit of time today to kind of explain what it means to be to be an explanation. So everything starts with definitions and facts. Okay, so you can refer to definitions in my notes. Um, that would usually be a good starting point. And then the final part would be the actual answer that you put into the exam document. So in between would be the logical reasoning. How do you start with the knowledge that we have talked about in this class, and step by step, logically derive, the answer? How do you know that is a 0 over there, based on what we have already talked about in class? So that's kind of what the explanation is for. Is it is a link. Well, I shouldn't say link. It is a chain. Okay, going from everything that we have talked about in class to the actual answer of the question. And the reason why I said it's not a link because it is a chain, which is a series or sequence of links. So then that it might involve multiple steps. To answer Joshua's question, yes, it is open book and it is open notes. It's open YouTube even. So if someone says, I vaguely remember tax says something about blah 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 on a certain day, and I would like to go back to that video just to be sure, that is perfectly okay, not a problem. And then there's another question. So with the work, we will be getting partial credit. Not guaranteed. Only if the work that is correct. Okay, because somebody from another class asked me about that. It's like, so as long as we show work, do we get partial credit? No, not guaranteed. It's only if the work is correct. It is working toward correctly to the answer. And yes, so the second line or the second part of the sentence is correct. So if you are in the right line of thought, um, then you are likely to get partial credit, but I cannot guarantee because where do I draw that line? Of okay, there seems to be something related to the answer as opposed to oh, this is definitely the right line of reasoning, and somebody just made a careless mistake somewhere. Okay, so I have to draw that line somewhere. Okay. So more on that on Monday. Okay, so I want you guys to work on the practice exam, just so that you can understand, what kind of format, last semester got for exam one. So your exam may not look like that. So, I have not yet decided what kind of question I'll be asking this semester. But, I just thought, instead of giving you nothing, giving you what I actually used last semester may be helpful. All right. So with that out of the way, we are now back to floating point numbers. But before we get to that, I would like to show you a document. Oh, not yet. Not this one, but I want to show you the syllabus because first of all, I'm assuming all of you have read the syllabus, which is super important. Oh, it's right here. There we go. All right, so I'm going to skip a whole bunch of stuff here and focus on this part here. So this course is transferable to UC and CSU. If you look up assist.org, that will tell you, which UC and which CSU will accept this class as an equivalent class to whatever they call, assembly language programming or whatever, okay? Because that's really just a name. But more important is the CID, course ID. This is Comp 142. So when you look up, Comp 142, and let me see if I can put this here. There we go. All right. So Comp 142, which is basically a more abstract, very loose outline of what this class needs to talk about. It doesn't even mention assembly language programming. Descriptor title is computer architecture and organization. In other words, when people call this class assembly language programming, it is a misnomer. That's just coming from way back when people actually only talk about assembly language programming. So the general description includes the mapping of statements and construct in a high-level language onto sequences of a machine instructions is studied. So we will get to that part. Okay, we will get to that part to the point that we'll be implementing recursive subroutines in assembly language. So we will get to that. But it also mentions, as well as the internal representation of simple data types and structures, numerical computation is examined. So the adding and subtracting, the binary addition, binary subtraction, that is numerical computation. How we compare, that is numerical computation. So that kind of gives you an idea why I'm teaching the class the way I'm teaching this class. And if someone else is teaching this class in a different way and they only talk about assembly language programming, they are not addressing the entire description over here. So I just want to bring this to your attention if you are wondering why this class, which is a computer science class, is touching on architecture stuff like logic gates and stuff like that. All right, so that's out of the way. Now we will close this window and back to the discussion of scientific notation. So as Paul indicated in the previous class, this is actually called the E notation, but I'm still going to call it the scientific notation, just because when we actually express scientific notation in C and C++, this is how we do it. All right, so now we're going to talk about this. We talked about this part already, how a value is represented, which bit position is used for what purpose. So unless there are specific questions about this earlier section, I'm going to move on to talk about um, how we can start to convert from base 10 to base 2 in terms of scientific notation. Are there any questions? I'm going to pause so that people have a chance to ask questions. All right. I am not seeing any questions, so I'm gonna move forward. This whole thing here is called a regular expression. Um, I'm not sure how many people have exposure to regular expression. It is very, very useful in programming. In web programming, it's really quite useful. Anything that involves your text processing, regular expression is extremely useful for just all of that stuff. If you want to perform certain tricky operations within an editor, knowing how to use regular expression can also be very useful because now you can pattern match things that are not exact because you're specifying a pattern instead of the exact string that you want to match. So regular expression is just a language so that we can specify a pattern. Can we get examples of this? Yeah, we'll definitely look at some examples. Definitely. All right, so let's go ahead and find out, how to read this really cryptic, or at first glance, if you have never have any exposure to regular expression, I understand this can look very confusing. So we're going to break this down one by one, step by step, so that we know what it is for. So we'll start with this part here. Everything in square bracket is are alternatives of one single character position. So in this case, I'm specifying, plus minus are the only two characters that can be specified in this space. Okay, so square bracket is indicating what characters can be used or options for this specific character position. Then we move on to backslash equal to. Backslash equal to is indicating whatever is immediately prior to it is optional. In other words, we can have 0 or 1 occurrence of whatever is right before that. So when you combine the square bracket plus minus close square bracket backslash equal to, all that is saying is a scientific notation can start with a plus symbol, it can start with a minus symbol, or it can start with none of those two because it is optional. So do we have any questions about this part of base 10 scientific notation? We can start with a plus, we can start with a minus, or we can start with neither of those two. Okay, I'm not seeing any questions. Next. So the next item is bracket 1 dash 9 close square bracket. So as you probably would imagine, that simply specifies the next character position has to be one of the ASCII code from 1 to 9. That's all it's saying. Cannot be 0, okay? Because if it were 0, then we don't have a normalized mantissa. So it has to be from 1 to 9. Because in the previous class, we already specified that the mantissa has to be greater than or equal to 1. So that means it cannot be starting with a 0. All right. I'm not seeing any questions. Okay. So what comes next is an entire group. When you see backslash open paren and then backslash and paren, that specifies a group. So when we specify a group itself, the group itself can have any number of characters. So now let's focus on what is inside the group, and then we'll talk about what are we going to do with the group itself. So inside the group, we start with a backslash dot. The backslash dot is simply saying a dot. Okay, it is simply saying a single period as a character. And then we have backslash d. Backslash d is a digit from 0 to 9. So backslash d is actually identical to 0-9 in square bracket, but it's just a little bit easier to type. That's all that is. And then the asterisk symbol over here is also a quantifier. It specifies whatever is immediately before it, or whatever is immediately to its left-hand side can have any number of, including 0. So that means this part here is by itself a small group. It means you can have 0 or more occurrences of a digit, and that digit can be from 0 to 9. So that's what this part is saying. And then the period is, so when you read this entire thing, it is, oops, sorry, I need to select the right portion. So when you look at this particular portion, all it says is you can have an optional decimal point followed by any number of base 10 digits. Okay, that's all it's saying. So when you look at the entire group, which starts from here and it ends here, it is also followed by a quantifier, which is backslash equal to. And remember, backslash equal to says whatever is immediately prior to it can have 0 or 1 occurrence. So that means if you don't have a decimal point and then a whole bunch of digits after the decimal point, that is perfectly okay as well. So that's basically what this part is. And after that, we also get another group, which is starting with the backslash open paren and is closing with backslash close paren. So now we want to see what is inside this particular group. So the first one is E, and that literally just means E in lowercase as a single character. And it's followed by plus minus in square brackets, which means the next character is either a plus or a minus. But wait, there's more, because we also see the backslash equal again. So that means the plus minus is also optional. So E may be followed by a plus, E may be followed by a minus, or it may be followed by neither of the two. And then after this group, which is optional, after the optional plus minus, we have backslash D again, which is a base 10 digit. And then this time we have a different quantifier. Backslash asterisk is a quantifier that specifies 0 or more occurrences. Backslash plus means 1 or more occurrences. So that means we need to have at least one base 10 digit after the E, but possibly more. So when you look at this entire group, it is followed by a quantifier, the backslash equal to, which is the optional quantifier. So that means the entire part that specifies the exponent of 10 is also optional. So if you just say 4, that's perfectly okay as a scientific notation. When you say 4E5, that is also a scientific notation, and so on. And okay, so there are some questions in the text channel. What does it mean it can be followed by neither of the two? So that means E doesn't have to be followed by a plus, E doesn't have to be followed by a minus. It can be followed immediately by a single base 10 digit, which is specified here. All right, so we're going to go through a few examples, okay, just to make sure that we understand how the regular expression works. And to do that, I am going to move this regular expression to the top of the screen like that, and then we'll get back to the tablet. So this way I can explain how it works, in handwriting. All right, there we go. All right, so we are going to start with something really simple, like that, okay? Is that being matched by the regular expression? The answer is yes, okay? It doesn't start with a plus, it does not start with a minus, but that's perfectly okay because this specification here says the initial sign for the entire number is optional. The optional part is because of the backslash equal to. So the 3 is going to match 1 to 9. And then this entire thing, which is the decimal point and some digits after the decimal point, it is optional, which means I don't have to have it. And then the E part is also optional because starting from here all the way up to here, the specification of the exponent in base 10 is also optional, so I don't have to have it. So 3 by itself is perfectly okay. Next, we look at 3.14 just by itself. So 3.14 is also okay. It does not have a optional sign, to precede the entire number, but that's okay because the sign is optional. It does in this case have a decimal point which matches this one here, and then it can have any number of base 10 digits after the decimal point. In this case we have 2. Well, 2 is fine because we can have any number of those. But then the E portion is optional, so we don't have to have the E component here. Let's try another one, which is 2 point, okay? Without any digits after the point. That turns out to be okay as well, because the 2 is going to match the 1 to 9. The point is going to match this point over here, but it is okay not to have any base 10 digits after the point, because this regular expression specifies that after the point we can have 0 or more base 10 digits. So 0 means, well, we don't have to have any. And then we can have 2e plus 5. Okay, this one is also perfectly okay. The 2 is going to match 1-9, and then we don't have any decimal point for the mantissa, nor any digits after the decimal point. And then we can have the optional e, so it does, this e is matching this e over here. And the plus is optional, but that means we can have the plus, and then we must have a single digit, at least one digit after the e, possibly having the plus and minus in between. So the 5 is matching that, the requirement that we must have at least one digit, and so this is perfectly okay. So let's take a look at what is not okay. Okay, so this is not okay because the 1 is going to match one of these things, but the 1 cannot follow by another base 10 digit. If it is followed by something, it has to be either a decimal point or an E. It cannot be followed by a base 10 digit immediately. So 10, it's actually not okay. And it is reasonable because the mantissa has to be less than or equal to, has to be less than the base. So since we're dealing with base 10, 10 is not less than 10, so that's why this is ruled out as a quote-unquote normalized scientific notation. Are we doing okay so far with this explanation? I think you guys are getting a general idea of what is acceptable as a scientific notation, at least under these rules. And someone may be asking the question, what are the chances that we actually have to understand syntax specification or regular expression in computer science? I would say pretty likely, because this is how programming languages are specified, and regular expression is one of the simpler syntax specification because it is recognizable by a finite state machine. When you're talking about the syntax of an actual programming language, not just to specify a number, but with constructs like conditional statements and whatnot, then regular expression cannot even do that. You cannot use regular expression to specify the syntax of C or C++ or Java or any sane programming language. Because in order to do that, you have to use a different class of language specification. Some of you will get into a compiler class, once you get into a 4-year university, then you will start to learn, what is a LALR1, language, and so on and so forth. I'm not going to get into those, okay? So don't worry, this is not a class to talk about how to parse programs, but I'm only trying to say that regular expression is going to be useful if you are getting into computer science. So this is an exposure. I will not quiz you on regular expression. So I'm not going to give you a regular expression specification and then ask you, okay, what about this string here? Does it match that regular expression? Don't worry, that won't happen. But in this case, I am only using this to specify a how I parse a base 10 scientific notation. Because if you want to write a program to recognize a base 10 scientific notation, you kind of need to know what the rules are, and this specifies all of those rules. Are there any questions? Does anyone want to do this? Does anyone want to write a parser that can parse a base 10 scientific notation that is specified by this regular expression?
Yeah, I actually had a question about that because
Go ahead.
you put it down as an exercise right after this section
Yes, I did.
in the
Yes, I did.
so how should I envision this exercise? I'm getting an input as just a string
Yep, yep.
that
Mhm.
is an expression in scientific notation or a greater string in which I want to
So
identify such
you
an
can,
expression.
yeah, I think the easiest is to think about, you're getting a string, which is you can even assume the string is properly formatted so that you don't have to focus on catching mistakes and errors. And then the idea is really just to find out, where is the mantissa, where's the exponent of 10, and so on. Now, I wouldn't,
And
yeah, go ahead.
to out return a float from that, for example.
No, the idea is we don't want it to return a float. We want it to return, I'll give you an example. Okay, so let me switch back to, all right. So the rest of this module is about, how do we convert from a base 10 scientific notation so that it eventually becomes a double, becomes a IEEE double precision floating point number. Because that happens a lot, right? Because when people type on the keyboard, they type in base 10. So when they want to specify a value, they would use base 10 scientific notation. But internally, the program or the computer is binary. And the floating point unit, the FPU of your processor, can only handle IEEE double precision floating point numbers. So you have to convert what the person types or what is in the file, okay, you have to translate that into an internal representation, which is the double precision floating point number that we have been talking about since yesterday. So the rest of this module it talks about how to get it done. Now, if you say, oh, well, since we have access to log and power and stuff like that, we can use those math functions. Well, that is true. Okay, you can use those math functions, but then it becomes a chicken and egg problem. Okay, because to use those math functions, they utilize the double type. Okay, and so we are trying to convert a string into double, and in the process, we have to use functions, math functions that make use of doubles. It is not entirely chicken and egg, but I would like to avoid that. So the rest of this module talks about how we can use only integer arithmetics to do this conversion. Um, it is not an unrealistic restriction because if you have a processor that is relatively wimpy, such as an Arduino processor, and you want to perform this conversion, okay, you're given a string that is in base 10 scientific notation, and then somehow it has to be stored in IEEE double precision floating point number because that's what you need to transmit to another computer for storing, for processing, or whatever you need to do. The Arduino is going to cough. It's going to die if you say, okay, we need to first take the log of this, and then we're going to have a double multiplication, and then we're going to have an exponent over here, and so on. The poor little Arduino processor running at 8 megahertz with only 8-bit registers is going to take a long time to get it done. On the other hand, if everything is done using integer math, well, it's not too bad. Okay, it's actually quite doable. So this is why I'm focusing on this discussion of only using integer math. So how does that get back and relate to your question, right? How do we want to parse this a base 10 scientific number into initially? We want to store everything as integers, signed or unsigned. Okay, so I actually got this part done already. This is one of the homework, one of the labs slash assignment for later on. But I'm going to give you an idea of how that works. Okay, so let's switch to the tablet. And we're going to work with a number. I'm looking for my pen. There we go. So let's work with this number here, 1.23 E45. Okay, so this is 1.23 times 10 to the power of 45. So now the question is, how do we want to parse this, right? Because I want to parse this into just integers. Okay, so the way I parse this is already done, by the way, so you don't really have to write this code because I have done it already. So this will convert into M10, or the mantissa. Now I'm going to put mantissa in quotes because it really is not the mantissa anymore, but the mantissa is going to be 123 instead of 1.23. In other words, I'm preserving all the significant digits of the original mantissa, but the magnitude has changed so that it is no longer a fraction. Okay, there's no fraction involved in order to store the 1.23 because now it is 123. And then we have the EXP10, or the exponent of 10. So the exponent of 10 was originally 45, but because the mantissa now becomes 123, I have to account for the quantity of the mantissa is now 100 of what it used to be. So the exp10, in order to preserve the same value, is now going to be 43 instead of 45. So I'm still preserving the value being represented, but this time I'm only using integer values because 1.23 times 10 to the power of 45 is exactly the same as 123 times 10 to the power of 43. So that is what I need to represent, the number after the parsing. Is I have one, I shouldn't call it variable, but one member of a structure is remembering the 123, which is what used to be the mantissa, all the significant digits of the mantissa. And then we also have another part of the structure to remember the exponent of 10 being 43 to begin with. I know this is a really, really long and windy explanation, but is that making sense? Maybe. Okay, all right. So this is the value that we want to represent. Okay, so V is just a value. 1.23 times 10 to the power of 45 is a representation of that value. 123 times 10 to the power of 43 is another representation of exactly the same value. So after we do all the conversion, what we want is to have some kind of M, which is quote unquote the mantissa. Remember, for it to be an actual mantissa, it has to be between 1 and the base. It has to be greater than or equal to 1 but less than the base. So I'm only using the term mantissa in a very loose sense in this case. But m is going to be an integer. And I want to convert this so that it is m times 2 to the power of something. We'll call this exp2. So the question is, how do we get this done? Okay, because originally we are specifying some quantity as an integer of some power of 10. We want to convert it so that it becomes some quantity times some power of 2. So that is what we are going to talk about for the next 2 classes. Okay, now next class is going to be a review session. So on next Tuesday, we're going to continue this topic. And then after the exam on Thursday, depending on how much time we spend to talk about that particular exam, we'll resume this particular topic. So there's a little bit of interleaving because of the exam. All right, so let's go ahead and start with something that's relatively simple, and then we'll try to work ourselves to something that's more difficult. So I'm going to start with something that is super easy, which is 1.23 times 10 to the power of, um, let's make it super easy, like 2. Okay, that is easy. That's easy because this really is specifying 1.23 times 10 to the power of 2. And since we are going to represent all the significant digits, using a single integer, it becomes 123. But we have to make up for making the quote-unquote mantissa, 100-fold of what it used to be. So the exponent of 10 will have to decrease by 2, so it becomes a 0. And we are basically done, because now we can say, oh, this is the same thing as 123 times 2 to the power of 0. Because 10 to the power of 0 is just 1, so it disappears. So if we really want to specify something, in as 2 to the power of something, that is going to be to the power of 0. So we are done. Okay, so this is pretty easy. But there are things that are much more difficult. Okay, so let's try. This one is actually not easy. Okay, it looks simple, but it's not easy. Because if you think about 1.23 times 10 to the power of 45, our unsigned 64-bit unsigned integer cannot represent this value exactly, because we can only represent up to, I think last time we figured it out, which is 1.8 times 10 to the power of 18, or somewhere like that. Okay, this is way too big to be contained by a 64-bit unsigned integer. So now we have to figure out, okay, so what are we going to do when, there are not enough digits, okay, to represent, the original quantity. So we're going to have to think about a systematic way to handle this. So are we still doing okay? Does everybody understand where we are going? We are trying to convert a base 10 scientific notation into the IEEE double precision floating point format, and only utilizing integer math in the process. So that's what we're trying to do, and along the way we have a few tricks that we have to kind of recognize and understand, the importance. Okay, so I'm gonna switch to a new slide and talk about, some of those important tricks. So let's start with division. Okay, so the idea is we can use division in order to change the exponent, to try to reduce the exponent of 10 to a 0, because that's kind of what we want to do. So once again, let's start with 1.23, and this time we'll start with a kind of large e, so times 10 to the power of 30. So this is 123 times 10 to the power of 28. And somehow we want to, and we can always put in, times 2 to the power of 0. So somehow we want to, we have a lot of flexibility when it comes to the significant digits, but we want this 28 to eventually get down to 0. But in return, we can, change the power of 2 to something, so that the value being represented is still the same. Okay, so we'll handle one thing at a time. Okay, the first question is, how do we reduce the power of 10? Okay, well, that's pretty easy, because if we just multiply the quote-unquote mantissa part by 10, then we can decrease the power of 10 by 1, and then we can do it again and again and again, right? So I'm just going to work out the next one. But eventually, we'll get to a value over here, which is the mantissa, quote-unquote mantissa, that is just barely fitting within a 64-bit unsigned integer. Okay, because at some point it's going to overflow. At some point you can no longer multiply that by 10, because if you did, you will be overflowing. I should say overflow. You'll be running out of the range of a 64-bit unsigned integer. So now the question is, what do we do at that point? Okay, so we can end up with 1, 2, 3, a whole bunch of zeros, and this turns out to be the last. You can no longer multiply this value by 10 again. Okay, times 10 to the power of something. I cannot, you know, tell you what it is supposed to be. Times 2 to the power of 0. Okay, so at that point we are running out of digits over here. So what are we going to do? Well, we can always divide it by 2, right? So when we divide this portion by 2, then we just have to adjust this one, and turn it into a 1. We can divide it by 2 again, and then increase the exponent of 2 until there is room to multiply this portion by 10 again. Then we can reduce the power of 10 by 1 at that point. Not sure whether that is making a lot of sense or not. So I'm going to give you an example. I'm just thinking how to do that. The reason why I have to think about this one is because, one, I don't want to give you the solution of a lab that you're going to have to do, but I still want it to be, okay, I think I know how to do this. We're going to use online GDB. It's a great tool, okay, and we are going to just specify the, so we have, okay, remember we want to specify exactly 64-bit unsigned integer, so we're going to have to use stdint.h, so that this way we can refer to a type that will give us exactly a 64-bit unsigned integer. So we have uint 64 underscore t to specify an unsigned 64-bit integer. That's going to be quote unquote the mantissa. Okay, so we'll say this is the mantissa. And initially it is 123. And then we'll have a regular int to represent the exponent of 10, exp10. And initially that was 28 in our example. And then we'll specify exp2, which is initially 0, because this is the initial exponent of 2. Because 2 to the power of 0 is just 1, so we can always assume that as the exponent of 2. And then in the body of main, all I'm going to do is to refer to the variables so that the compiler does not optimize everything out. I'll show you what I mean by that. I'm going to set up a breakpoint over here, specify the programming language to be C, and then start to debug it. And obviously I have used JavaScript for too long. I'm missing all the semicolons at the end of each statement, because that is optional in JavaScript. Alright, let's do that one more time. Debug. Alright, so this time it does compile. The question is, do I still have access to the local variables in main? It says resource. It doesn't like it. We'll try it one more time. There we go. And we can see there are no local variables because they all got optimized out. Okay, so let's take a row first, and then we'll get back to this, and then I'll illustrate the general approach of doing the conversion from base 10 to base 2 scientific notation. Alright, so getting back to, okay, I just need to find one instance. There we go. Yep, that's the right class. Alright, so the word for row taking today is regx, which is how we usually write regular expression. But the quiz is not open yet, so I'm going to have to open that up. And the current time is 20, we'll call it 22, so I'm gonna give you guys up to 27. So it's June 17th, 6:27 p.m. All right, save and publish. So go ahead and participate in the road taking activity. I'm gonna do that too. So I just have to go to preview and okay. Yeah, it's just warning me that it's gonna be automatically submitted in 5 minutes. All right, it is supposed to be regular expression, regex or lowercase, and then click submit quiz, and voila, I'm getting 1 out of 1 point. Cool. So while you guys are doing that, I'm going to fix this program so that the variables do not get optimized out so that I can actually do something in the debugger. Alright, so type here. Mistyped. Okay. I will go ahead and fix that after the class. Next time, just copy and paste from Discord. Alright, so I'm going to assume everybody is done with the road taking activity. So we are going to get back to this program. So this is how I'm going to trick the compiler so that it does not optimize the variables out of existence. Because it just needs the variables to be referred to. Yep, doesn't like it. There we go. All right, so do we have our variables? The answer is no.
Isn't x2 being recognized as a function or something? There's a
X2?
different syntax coloring there.
Oh, EXP2?
Right.
Yeah, it colors it differently, but it's not, that is not the issue. It's just, the compiler is just being smarter than. Okay, so we'll. Oh, darn it. There might be a function called exp2 somewhere, but it should not interfere with me trying to name a local variable as exp2. So we'll go ahead and hard code it this time. There we go. So we get everything initialized. Save the program. Oh, nope. There we go. Yeah, I don't have to save the program. Saving it would make it usable again, but like in the future, but I don't need it. Alright, so let's go ahead and debug it this time. Huh. Nope, it is still optimizing everything out because I'm not referring to those things. Alrighty. Okay, let's make a useless variable here, and we'll just do something here to refer to every single of the local variables. So this way, hopefully, we can trick the compiler into thinking that it needs to keep those local variables around. And it's still too smart to to keep those variables around. Oh, that is frustrating. Yep, it understands enough to understand that these variables are not being useful. Oh, that is well, okay, so I can do something. Nah. Okay, the reason why I don't want to do this using a spreadsheet is because in a spreadsheet, a spreadsheet actually does not understand what is a 64-bit unsigned integer. Every time you specify a value, a numerical value, it is being stored as a double precision floating point number. So when we get to the point where we are running out of digits to store something into a 64-bit integer, the spreadsheet would actually, it won't give us the effect that we are looking for. So that's why I don't want to do this in a spreadsheet. All right, so I'm going to use my terminal for this part because it's just a little bit faster for me to use a terminal. And need to go find it first. There we go. All right. And we are going to okay, we can use a struct this time. So in the struct we have a member called the Mantissa. We'll just call it M, so it's easier to type in the future. And then we have a exp e10 as the exponent of 10, and then we have a e2 as the exponent in base 2. So now we can make a struct n, lowercase n or num, and now we can say num dot m is 123, num dot e10 is 28, num dot e2 is 0, and then return 0. So let's see if the compiler would optimize the structure out. I'm gonna guess it might, so we'll go ahead and just refer to one of the members because that should keep the entire structure around. All right. There we go. And then we want to put a breakpoint. Oh, the syntax highlighting is making the equal symbol really hard to see, but that's not going to be a big issue because we are not going to refer to the program much. So we'll put a breakpoint on line 18, run the program, and print num. There we go. Yes. So I can now trick the compiler to keep everything around. All right. So what we're going to do is we are going to adjust m until we can no longer multiply by 10 anymore. So the first thing we do is set var num.m multiply equal to 10, and therefore we are multiplying the mantissa by 10. And every time we do this, we are going to subtract 1 from e10. So set var num dot e10 minus equal 1. And then we have to double check, okay, to see whether we can multiply the mantissa by 10 again. So this is our first question. How do we know whether we can multiply the mantissa by 10 again? In other words, how do we know that we are just about to run out of range for a 64-bit integer. So I want you guys to think about it, because the next time I do this, I might end up with a value that cannot be represented using a 64-bit unsigned integer because it just keeps getting bigger and bigger. So the question is, how do I test whether I can multiply the mantissa by 10 again or not? So I want you guys to think about it. The size of m plus e10. Not quite sure what you mean by the size of, because size of usually refers to the number of bytes of a variable, and that stays constant. Anyone else? I'll let you guys think about it a little bit.
Could you just do a comparison of how many bits are in your
Aha.
your bit width, I guess, and then set that as
Okay.
2 to the exponent of your bit width, and then test see if
Okay.
smaller.
So how do you know now? Because when you multiply by 10, it is. So how many bits are we going to test? In other words, are we testing bit 63? Are we testing bit 62? Or are we testing bit 61? Or are we testing bit 60? Do you see what I mean?
That's a good question.
Yep. So testing bit position is not going to be helping us in this case because the multiplication is by 10, and 10 is not a power of 2. Now, if we were multiplying by a power of 2, then we could use the bit testing approach because we would know, which bit position we need to test. But because we are multiplying by 10, we cannot use that approach. All right. So let me go back to the tablet first because I want to talk about the general approach to do this. So the first thing we need to know is what is the largest value that a 64-bit unsigned integer can represent. That's the first question, because if we don't know how to express that, then there's really nothing we can do in this case. Okay, so the question is, what is the largest value of a 64-bit unsigned integer? Question mark. There we go. And there are many ways to get to this answer. We can start with the most obvious one, which is also going to be the most painful one. Because we know the largest value that can be represented by a 64-bit integer would be all ones when we look at it as a binary number. As it turns out, GDB does allow you to use base 2. And if I remember right, I think it's 0b or 0t, I cannot remember. 0b, there we go. So you can actually use 0b as a prefix and then use a whole bunch of zeros and ones after that to specify a Boolean, a binary number. So if I want to do it this way, it's going to be quite painful because I'm going to have to type 164 times. Okay, and I'm going to guarantee you that I'm going to miscount that. That is not going to be a viable approach. Okay, now if you have a really short or a value that doesn't take a lot of binary digits, it's perfectly okay. Okay, for instance, if you want to express 13, okay, but you want it to specify in base 2, it is 1101, works out perfectly. Okay, that's easy to do. But when you have to type 64 ones, this may not be the best way to do it. Okay. But some of you may remember, but Tech, didn't you talk about hexadecimal number like base 16? Because one base 16 digit is going to replace 4 binary digits. So instead of having 64 ones, we're going to have 16 digits in base 16. And F is 1111. Okay, the digit F in hexadecimal is 1111. So we can actually use that approach. Okay, so 0x is the prefix of a base 16 number. This works in C too, not just in GDB, but this also works in regular C. So now we can say, we will just need to specify 16 Fs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There we go. It does work. Great. But this may not be the best way to do it because typing 16Fs is actually prone to errors, okay? So I'm going to teach you a very obscure way to specify the largest value in as a 64-bit unsigned integer, and this is going to look very awful, okay? So, but I will present it anyway. So uint 64 underscore t, which is a typecast, and -1. You go like, what? I'm just guessing that you guys are going like, what? If you already know why this works, great, okay? But if you don't, that's okay too. Because if you think about the number wheel, remember that position that is immediately to the left-hand side of 0? In binary, it is all ones, okay? If you interpret that using the unsigned interpretation, it is specifying the largest value for unsigned integers. But if you use the signed interpretation, that always specifies -1 because it's only one slot to the left of 0. So it is always specifying -1. So why this trick works is because the -1, I should say, the -1 value, when you look at the binary representation, is identical to the representation of the largest value that you can represent in as a 64-bit number. So that's why this trick works. Okay. All right. So if this trick is going to work, then what are we going to do? Remember, the original task is to see whether we can multiply member m by 10 again, so that it does not exceed what we can actually represent. What about something like this? Okay, you guys tell me whether this is going to work or not. So I'm going to check a condition. I'm going to check and compare the significant digit of the mantissa against the value that we have specified here, which I'm going to say this is u int 64 underscore t minus 1 and divided by 10. So do you think this is going to be useful? This comparison, is it going to be useful? What does it mean when this is returning a 1, and what does it mean when it is returning a 0? In fact, let's just figure out what it is going to return in this case. Is it going to return true or is it going to return false? We already know what num.m is. It is 1230. So do you think 1230 is less than or equal to the largest value that we can represent using a 64-bit unsigned integer divided by 10? Come on, you guys know the answer. It's really obvious. 1000 something versus the largest value that we can represent using 64 bits and then divided by 10. The answer is yes, right? It's going to be true. There we go. What does it mean when the answer is false? That means don't multiply m by 10 again, because when you do, it is going to exceed what we can represent using 64-bit as an unsigned integer. Does that make sense? Okay, if that doesn't make sense, let's do some algebra. So the question is, if I multiply m by 10, is it going to exceed what we can represent using a 64-bit unsigned integer? This is what we want to figure out, okay? And we only want to keep multiplying m by 10 if the answer is false, okay? So, but we cannot do this comparison. This comparison makes no sense, because if we were to multiply m by 10 and it does exceed that range, it is not capable of representing that value, because because this is the largest value that this expression can actually represent. So it doesn't make sense to compare it this way. Well, if this doesn't work, what are we going to do? we're going to do some algebra. We will divide both sides of the comparison by 10. So one side is just 10, and then the other side becomes 2 to the power of 64, the whole thing minus 1, and then divide that whole thing by 10. So that is why in GDB I am doing this comparison. Now the comparison is the other way around because I want to see if I can multiply by 10. So if the answer is true, then I can multiply by 10 again. All right, so I'm not seeing any questions. So and we are not running out of time yet. So I'm going to do it like this. So I'm going to multiply m by 10 again, but every time I do that, I have to adjust the exponent of 10 so that that decreases by 1. And then we'll check to see whether we can go through another cycle or not. And the answer is yes, we can go through another cycle. So, and we can do it one more time. 1, 2, 3. Like that. So we're going to keep doing this until the answer is false. Alright, so it's going to take a while, and some of you probably can mathematically figure out how many iterations this is going to take. Not sure whether we can combine those three statements into one. Oh, because I missed one already. There we go. I really need to learn how to script in GDB. GDB is actually scriptable. So if you want to make your own test suite, to test a program, you can actually do it because GDB is sort of a programming language on its own too. It's quite useful, but I haven't used it for a while, so I can't do it right now. There we go. Now it is false. So let's go ahead and check out what num.m looks like at this point. Whoa, that is pretty big. So what this means is we multiply this by 10 again. It is going to be a value that we cannot fit into a 64-bit unsigned integer. So the question is, what are we going to do? Well, okay, let's take a look at E10 first, okay? E10 is now 11, so we got pretty close. We started off with 28 and we just want to get it down to 0. But we can no longer keep doing this, which is making m 10 times as large as before and then decrement E10 for every single iteration. And that's because m is already maxing out what we can represent using a 64-bit unsigned integer. So what we need to do is to make room for that, okay? So how do we make room for that? We can divide m by 2 and then increase E2 and then keep doing that until there's room to multiply m by 10 again. Okay, so I'm going to show you what that means. So right now I'm not going to take rounding into consideration. We'll talk about rounding, maybe in the next class, but I'm not going to talk about rounding. So what we need to do now is to say, let's not multiply by 10 anymore. Let's instead divide it by 2. But every time we divide m by 2, we also have to remember to increase E2 by 1 so that the quantity being represented is not changed. Okay, and now we have to test again. Okay, we have to go through that test to see if m is now small enough so that we can multiply it by 10 again. The answer is nope, not quite. All right, fine. We'll divide it by 2 again and increase E2 by 1 again, and then go through that test again. Aha, now we can do it again. So now we can go ahead and divide divide m by multiply m by 10 again, and then decrease e10 by 1 again. So we'll do a set var num.m times equal to 10, set var num.e10 minus equal 1. There we go. And we'll check to see if we can multiply m by 10 again. Can you guess what the answer is going to be? We just barely had enough room to multiply m by 10 again, and then we did. So do you think we have room to multiply m by 10 again right after that multiplication by 10? The answer is no. Okay, the answer is we are not going to be able to do it, but we can check, right? So we can't do it. So now we have to divide m by 2 and then increase e2 by 1. And then we can test to see if there's room for another multiplication by 10. And I can tell you the answer is not, it's going to be no. Because 10 is greater than 2 to the power of 3. So we need to divide m by 2 at least 3 times to have a chance of having enough room to multiply by 10 again. So definitely not. Another time. And not yet. Okay. One more time. And I think it's still not going to be enough room this time because last time we shifted 3 times. This time it's going to have to shift 4 times. Yeah, so it's not time yet. So do it one more time. And check again. And this time we have room to multiply m by 10. And therefore we can decrease e10 by 1 again. So let's take a look at the entire structure. So the m is now this particular quantity, and e10 is now 10, which was 28 to begin with. So we took care of a whole bunch of exponents of 10 already, and then e2 was 0 to begin with, and now it is up to 6. So you can kind of see what we are doing here. Okay, we are trying to keep m as large as possible. But when it is no longer possible to have another multiplication by 10, then we keep dividing it by 2 until there is room to multiply by 10 again. But then every time we multiply m by 10, we decrease e10 by 1. Every time we divide m by 2, we increase e2 by 1. So by doing that, eventually, we are going to decrease e10 all the way to 0. And for all practical purposes, the conversion is quote unquote done at that point. Because after that, okay, taking care of m so that it is actually normalized, getting rid of the 1 point, and then also figuring out the right biased exponent of 2, those are like really mechanical. Those are really easy operations to perform. It is this process that is a little bit harder and a little bit tricky to do. Oh, it is 6:50 right now, so I am going to stop this particular line of lecture.
I have a question.
Yeah, go ahead.
So do we need to change the negative? Where is -1 divided by 10, or
do we need to
we
change?
stays? I'm saying the -1. You see -1 divided by 10, where you change the e to the 2 plus is equal 1. You change that to the positive 1, right? Do you getting what I'm saying?
Not quite.
So you change it to the you see the said var num e2 plus is equal to 1. You change the -1 to 1, positive 1, right?
Wait. Where is the negative 1 coming from?
From the e10 to negative is equal 1, and then you change it to positive.
What?
Do you see the e10? Num
Yes.
e10 negative, you change it to the positive, right? Bottom
yes,
e2.
but do you understand why we do this? Do you
I
understand
do, but
the relationship between multiplying the mantissa by 10 and then decreasing the exponent of 10 by 1?
Yeah.
So this is really doing
Question.
the same thing, because when we divide the mantissa by 2, we have to increase the exponent of 2 by 1 so that we are still representing the same value.
Okay, my question was, so we don't change any number between the unit 64 between that, right? We just change the top number.
I'm not sure what you mean by the top number.
You see the print num?
Yes.
M is equal to unit, where then and we have -1 divided by 10. We don't change the -1 or not?
I'm not sure what you mean by -1.
Do you see we have -1 number?
Maybe I think I see what he's talking about. He's talking about the comparison to the largest
Okay,
int
so
64 unsigned.
yeah, so this part is only is specifying the largest value that can be represented using a 64-bit unsigned number, and we have to compare it to that value divided by 10, because if m is less than or equal to this value, then we do have room to multiply m by 10 again. Because the
I got it.
idea is I don't want to run out of range when we multiply m by 10 again.
Oh, okay, got it now.
Okay. All right.
Thank you.
All right. So we will get back to this. Okay, we'll get back to this, but this is a fairly good demonstration of what your program will need to do when we get to the conversion part. So you're going to write some C program, okay, for this portion of the class. But right now we are backlogging, a little bit in terms of lab activities. So we are now going to go back to do the binary subtraction and comparison lab, which is this one. And let's see, we'll go to edit so you can see the access code. All right, so here's the access code. It is flags. Right here, I'm going to copy that to the text channel. So flags is the access code of the lab, and the lab is going to be due tonight at 8:20 p.m. So today is June 17th, 8:20 p.m.
Professor, could we get an extra 5 minutes on that since we ran a little bit over into the lab, or no?
Sure, 5 minutes.
Thank you.
All right, and save and publish. And by the way, you can reattempt several times, as many times as you want before 8:25 p.m. And it only counts the highest score. So you can, if you don't get a perfect score the first time and you have plenty of time left, you can go ahead and try again. All right, and I think this one is not super duper complicated, but it does, go back to the topic of subtraction and compare. So you can still look up the notes and try to use that to help you. All right. All right. So unless there are questions that I need to answer for the entire class, I'm going to stop live streaming and stop screen sharing.
Just need the code, Professor.
Huh?
So.
Oh, never mind.
The code is in the text channel.
So after this, we can just hop on off. This is all we have to do.
Yeah. Yep. That's true.
All right. Thank you for your time, sir.
All right. You're welcome. So I'm gonna sign off, and I'll be back in about 10 minutes.